Okay, we'll begin today by looking at cyclic groups again, but now we'll use Lagrange. And again, some of this we had talked over in the face-to-face meeting. So first of all, we have the infinite cyclic group. Before we do that, let's just review a little bit about the cyclic subgroup. This is the basic building block. We set A, where it's equal to, in general, A to the n, every integer in Z. This would be A is an element of the group, G is the group. And so there's two cases of what this happens. So this is repeated operation of the group of an element applied to itself. That's what's a positive. So what's in this group? First of all, there's one thing that this is the smallest subgroup in the sense that if H is a subgroup of G and A is an element of H, then we must have that this set is a subgroup, or just, well, we already know it's a subgroup, is contained in H, which is equivalent to it being a subgroup in H. So this is all powers of A. Think about why this would make sense. What would you need to have A? Well, you need A squared, you need A cubed, etc. A to the all keep going all infinitely many positive powers of A. You need the identity. Well, that's A to the 0 is the identity. And you need the inverse. So that would be A to the negative 1. And then if you have the inverse, you have to have the inverse times the inverse. That's A to the negative 2. So that's why you have all integers. And we'll see what happens in the finite case, but in the infinite cyclic group case, it's basically all like Z under addition. Where Z could be the infinite subgroup generated by 1, or we could also generate it by negative 1. Where now this subgroup would be 1 plus 1 plus 1 n times. For n integer. So here, you don't take powers of it, obviously, you would just get 1 no matter what the integer is, because this really means the element applied to itself repeatedly in the group operation. So for the integers under addition, we've already seen and proved a little bit about the subgroups, that every subgroup is of this form. So this is only if X is an element of Z under addition, then this means multiples of X. Positive and negative and 0 in X. So that's kind of the story of infinite cyclic groups. If you remember, I think we proved that if H is a subgroup of it, then by using the well-ordering property, picking sort of a least positive element of it, that actually generated it. And all subgroups of the integers are cyclic. And that's really any infinite cyclic group essentially is exactly like Z. So we have that. So we'll get that out of the way. Now we'll focus on finite cyclic group with the final remark, just that, notice here we actually have to take negative 1 times Z, or negative 1 times 1, or in general negative 1 times X, and 0 times X to get the identity and the inverses in it when you have an infinite cyclic group. So that's why it looks like a little bit different concept. The finite cyclic group, as we've seen, and we'll see some more, they just keep going to a certain point, then they hit the identity, and then you stop. And so just as a reminder that the order of an element G in a group G is just the order of its cyclic group generated by that cyclic subgroup generated by that. And so really two things happen. You either keep looking at positive powers of A, and either you get back to the identity or you don't. So when you get back to the identity, then you've got a finite cyclic group generated by that element. And that element would have some finite order. If you don't get back to the identity, then you have an infinite cyclic group, and you can't just add or repeatedly apply the element to itself. You've got to throw in the identity, and you've got to throw in the inverse of the element, and you've got to throw in adding the inverse of the element to itself repeatedly. Or when I say adding, I'm thinking of the integers. In general, applying the group operation to an element in itself. So again, in symbols, we have the order of G equals the order of H. So by Lagrange, the order of G divides the number of elements in H for all G and G if the order of G is a finite number. So the claim is, so why is that? Before I make my next claim about another fact, why is that? This is the same as the order of this cyclic subgroup. This is a subgroup of G. So by Lagrange, the order of any subgroup, cyclic or otherwise, divides the order of G. So that makes sense since we define the element of an order, the order of an element by the order of the cyclic subgroup that element generates. Then Lagrange, this comes right out of Lagrange immediately. And we may have proved this earlier, but just the claim given A in G, if the order of A is finite, then the order of A equals M, where M is the smallest positive integer such that A will get back to the identity. And again, the proof of this, we're going to use some of the division algorithm, and we're going to use some of the structure of the integers to help us analyze what happens with the exponent, and that will help us analyze the structure of the group. So that's sort of the idea of the group theory and abstract algebra in general, trying to generalize some of the notions of arithmetic in basic arithmetic to a higher structure. I think we've looked similar to this. If the group is finite, we know this set is non-empty. That's probably what I'll show first after I erase this. So let's look at this claim. So this set is equal to this set, which is n, say a finite number, what we have is by the pigeonhole principle, we have some j and k, we have two integers. And they're unequal, so one's bigger than another. I think I put, let's follow my notes, let's put k greater than j. And a to the k equals a to the j. Because there's infinitely many integers, so there's infinitely many a's to integer powers, but there's only finitely many distinct elements in the set. So two of those have to equal. So if we divide out by j, or properties of exponents multiplied by a to the negative j, we would be left with the identity. Basically, we divide each, in a sense, we're dividing each side. Well, let's not say divide, let's multiply by the inverse of j, the inverse of a, j times to each side. So if we have j factors of a multiplied by the inverse of a, j times, this would cancel out. And here we would subtract this. This is k minus j is positive because of our assumption. If not, we could just switch it, call the other one k, and then j, switch the labels. So that's what without the loss of generality. So that tells us this set is non-empty. So the set of m's or k's, whatever integer you want to use, m's, so such that a to the m is equal to the identity is not empty. So it has a minimum positive element. Right, the set of all positive, and I should maybe be that clear, the set of all positive sets. That's my claim, right? That it's the least positive integer such like that. So call this least element m. And what we want is we want to say that m is in fact the order of it. So what do we have? So first let's show that the order of this cyclic subgroup is at least m. Well, certainly this cyclic subgroup contains a or a to the 0, which is the identity, a to the 1, a to the m, and I claim or has the elements of this set are all different. Just erase, so I claim that the cyclic subgroup generated by A has at least m elements. I claim that set has m distinct elements. It certainly has m elements, but are they distinct? If not, I had, what did I have? I had A, R would have to equal AR prime for R not equal to R prime, and both would have to be between m minus 1 and 0. But again, we'll do another loss without loss of generality. So one of those has to be bigger. Let's call the bigger one, I think, let's follow my notes, R. So R has to be bigger than R prime. And so again, a very similar argument to what we did before, A to the R minus R prime would have to equal the identity with that's a positive number, but that's less than or equal to m minus 1, which is less than the minimum of such positive number. So that's a contradiction, since r was the minimum positive number. So what does that tell us? That tells us that those elements are all distinct. Or as we indicated, if those elements are all distinct, there's got to be at least m different elements in that set. Now let's show the other inequality. Let's show that, on the other hand, there's no more than m elements in the set. So I think for that, we're going to appeal to the division algorithm. And so what do we have? We have, let's show that this is less than or equal to m. So if we take any a to the k in the cyclic subgroup, so that's k can be any integer. We know there exists a q and an r. I've used r already, different letter, maybe use s. S is going to be like our remainder in z with and I'll just jump right to the division algorithm with a to the k. Well, k is just going to be a to the, say, let's divide it by m, qr plus s. I should say qr, and so s is your remainder, so s is between strictly less than n, or less than or equal to 0, or less than, strictly less than n, so less than or equal to m minus 1. And then by doing some properties of the exponents, this is just going to be a to the m raised to the q times a to the s. But this is just the identity, the q times a to the s. So this is just a to the s, and s is between 0 and n minus 1, so it's certainly in this set. So therefore, any element in the cyclic subgroup has to be one of these n minus 1 elements, so they can't be, sorry, this goes to n minus 1, but I have 0 here. It has to be one of these m elements, so that means that there can't be any more than m elements in that cyclic subgroup. And so that both inequalities together prove the theorem. That the order of the element A is just m, where what is m is the least positive integer. That brings us back to the identity. So we're going to look at some more divisibility relationships and try to find the order of a cyclic element. Okay, so again, what we've proven is the order of an element of a cyclic subgroup is going to be the least positive integer that takes you back to the identity, if there is one. If there is not such a positive integer, then it's just the order of the cyclic subgroup. Then it's just infinite. We have infinite order. So we'd like to find out what, in general, how to generate a cyclic group. Kind of a project given G a group with A an element of G. If we have an element of finite order, find the order of A raised to the S for S any integer Z. And so what we end up showing is the following. And so let's complete this project. This is going to be the order of the element over the greatest common divisor of S and M. So that's the theorem with this setup. And I'll even state the corollary, which comes out of the proof, is when are powers of A going to be generate the same subgroup when they have the same greatest common divisor of M, the order of the element. So then A to the S would have the same order as A to the T. So this, I think, comes out of the proof of what we did. So it's a corollary, not necessarily of the statement of the theorem, but of the proof of the theorem. That's why I mentioned it before. So we're split into two cases. If the GCD of S and M equals 1, we claim, well, M divided by M would be, GCD of S and M, if it's 1, M divided by 1 would be M. So we claim that the order of A to the S would equal M. So since A to the S is A to the S, that's certainly a power of this. So A to the S is in the cyclic subgroup generated by A. That means the cyclic subgroup generated by A to the S has to be inside the cyclic subgroup generated by A. Oh, let me say why. Oh, I see what this is. Since, what's it, well, I guess that would be it, right? Maybe if you need another detail, why, note if we look at A to the S to the K, that's A to the S times K, so that's, A is some integer. A is some integer, so A to the SK is certainly a power of A. But even in general, if an element is in the cyclic subgroup generated by one element, then certainly the cyclic subgroup generated by that element has to be inside this. Because this is the smallest subgroup that contains A to the S, and A, we've just shown that A is one subgroup that contains A to the S. So this is just sort of a review. This is really not necessary, because once I show A to the S is inside the cyclic subgroup generated by A, this fellow right here, then we know this subset this is the smallest subgroup that contains A to the S, so that's got to be inside. So what do we do? I think GCD, I think two integers. That give us 1. So then A, which is A to the 1, or A to the alpha m plus beta, something is amiss, the GCD of S and M. So let's make this S and this M. But if we simplify, this is A to the S to the alpha times A to the M to the beta. But as before, we've seen A to the M is the identity. So this is A to the S to the alpha and A to the S raised to the alpha is in the cyclic subgroup generated by A to the S because it's A to the S raised to some integer. And that's how that set was defined, right? It's all, this element here, it's all integer powers of that. So A to the S, so A is an element of the cyclic subgroup generated by A to the S. But since the cyclic subgroup generated by A is the smallest subgroup that contains A, this has to be inside. So we've got double containment. We have the cyclic subgroup generated by A. And so the order of this would, A to the S is equal to the order of A, which is just M, which is certainly M over 1. So that proves the theorem in the case of the greatest common divisor of the power S and M is equal to 1. So what happens in the other case when it's not 1, when it's some positive number? So we'll see, I'm looking through the notes here, this should be strictly greater than 1, not 0. So let's look at case 2. Case 2 is equal to 1. So second case, the GCD of S and M is some number D, which is strictly greater than 1. But by Lagrange we have, well, not even by Lagrange, we have just by the definition of the greatest common divisor, we have D divides M. So M equals dk for some integer in Z. And so what I claim then is D, I claim that the order of A to the D is equal to K. Which, why am I doing that? Well, that's what I want, I think, because what is K? K is equal to M divided by D, but what the heck is D? D is the greatest common divisor of S and M. So we have that would then hold. Okay, so let's see why this is the case. Certainly we have a to the d raised to the k is equal to the a to the k, a to the n, which is e. So k certainly k is a positive number. And this really says that the order of a to the d has to be less than or equal to k. But let's argue by contradiction. Suppose there exists a k prime that is positive, that is strictly less than k, and yet a to the k prime is the identity. So what does that mean? That means dk prime would have to be less, if k prime is less than k, dk prime is less than dk, which is equal to m. But then if I look at a to the k prime d, okay, that's a to the k prime raised to the d. But a to the k prime, if we assume that there is such a k less than k prime, that takes you to the identity, a to the k prime would take you to the identity. So that would just be the identity with this less than m, which is the order of a. So that's a contradiction, because the order of a is the least such positive. Right, certainly this has to be positive. Why? Well, k prime is positive and d is bigger than 1, so k prime times d is certainly positive. So I think that contradiction really proves it, right? Because therefore no such k prime can exist. So k has to not only be one exponent that took a to the d and made it equal to the identity, but it's the least such positive exponent. So this contradiction means there can be no such positive z or such k prime and what was the contradiction really came from assuming k prime is less than k. So k is the minimum or the least, I like least such positive integer. That means the order D has to equal that K as required. Okay, and then I mentioned the corollary. This, or what's the corollary say? If the GCD of S and the integer m is equal to the GCD of T and the integer m, then what happens? Then we showed in the proof that AS really is the same as AD. That's how we did it, right? That's why we got the order. We showed that the cyclic subgroup generated by A to the S is basically going to be equal to this AD. So what we have then in this case, if we have this additional assumption, this A to the S is going to be the same as the GCD of S and M. But if those two GCDs are equal, they are equal. And again, by what we showed in the theorem, or in the proof of the theorem, that's equal to A to the D. Right, because we've shown that the order of A to the D is going to be the same as the order of M divided by S over M. Okay, actually, I think I need to go on and let's examine why this is true. I think we still need to also decide and look carefully what we prove here. That's not really what required. That's what we've shown, that the order of D is equal. I'm looking back at the statement because that wasn't what the statement was, though. So let's go back a second. So we've shown that the order of D is equal to this K. So the order of A to the D is equal to K. But let's prove this. Let's look some more. Let's look at A to the S over A to the D. So what we would have then is certainly S equals D times T for some integer T. So that means what? That means A to the S is A to the D raised to the T, which is an element of the cyclic subgroup generated by A to the D. So A to the S is inside this subgroup. So the smallest subgroup that contains A to the S also has to be inside that subgroup. And there's kind of two equivalent ways of calling what this symbol means. You can think of this symbol as a cyclic subgroup generated by A to the S. You can think of this symbol as being the smallest subgroup of G that contains A to the S. What about the other way? I think we have to do again some the GCD inclusion order. Which, again, maybe that's what I need to do. So maybe we did prove some of this. But let's look at it again. AS plus alpha BM. AS to the alpha. We've already run through this, so this is just going to be the identity to the beta, so just the identity. And this is an element of A to the S. So this A to the D is inside this subgroup, so the smallest subgroup that contains A to the D has to be inside of here. So now we've got this conclusion. Okay. So that really completes it. So before, what I had proven was the order of A to the D equals that. But now what I've proven, since those two cyclic subgroups are the same, the order of A to the S, by definition, is the same as that cyclic subgroup generated by A to the S. But we've just shown that's equal to A to the D, which was the order of A to the D, and what I just concluded here, that's equal to M or K, which is just M over the GCD of S. So what I did before, actually, when I said completes the proof as required, I really didn't. I proved my claim, but I have to backtrack a little bit. How does my claim answer the original theorem, right? The theorem wasn't that A to the D, wasn't that A to the GCD of S and M is equal to K with that. It was that A to the S was equal to this fraction. And so that completes the proof. And so now, if both these elements S and T, different T from in that divisibility relationship here, because the greatest common divisor is one divisor. But if there's two integers that have the same GCD with M, then we've shown these two subgroups are the same. So that proves that the order of A to the S is equal to the order of A to the, or basically these two elements have the same order. So A to the S, so this is A to the T is what I want to say here, right? So this applies for any integer, right? A to the T has the order of the GCD of T comma M. But if that's the same as the order of S comma N, these are two equal quantities. And then by what we've just proved over here, the order of A raised to a power is equal to the order of A to the greatest common divisor of S and whatever the order of A itself is. Okay, so let's go back now to the main theorem of cyclic groups, and we'll state that and look at some examples. And hopefully that gives a little more insight into how cyclic groups work and what they are and how they relate to the order of an element. So again, you've got this concept, the smallest subgroup how many elements are in the smallest subgroup that contains an element? What's the smallest integer where that element raised to that power equals the identity? Those two concepts coincide. So let's now prove the main theorem of a finite cyclic group. Let me just state without proof an infinite, well, I'll get back to the infinite version now. Let me just state, won't even write it. We looked in the notes on the integer, the subgroups, we first showed that every subgroup of the integer is an infinite cyclic subgroup except the subgroup that contains just 0. This is the integers under addition. And that's true for an infinite cyclic group. For an infinite cyclic group, every subgroup of an infinite cyclic group is cyclic, and apart from the one element subgroup that just contains the identity, every subgroup of a cyclic group is also an infinite cyclic group. What about a finite group? So let's go main theorem of finite cyclic group. Well, if G is a cyclic group, G has to be generated by some element A, be a finite cyclic group with the order of G equals n. Then all subgroups of G are cyclic. And there exists exactly one subgroup of order k for each divisor k of each divisor k of n. So let us begin the proof of this. Let H be any subgroup. So we actually, now since A is finite, we can list all the elements of A. There's the identity, which is A to the 0, A to the 1, A to the n minus 1. Let's remark right off the bat, H must be finite. So if the order of H equals T, by Lagrange's theorem, T divides n. We even use this, so I think this comes later on in the proof, but let's just stay right off the bat. We now have Lagrange established, so let's make that note. So let's look at H. So what do we have with H? Well, H certainly has A to the 0. It's a subgroup, it has the identity. And then there's a first element, a second element, and finally a tth element, A to the S, T minus 1. Again, 1, 2, T minus 1 elements, plus this. And by arranging these labeling systems, we'll pick S1 to be the smallest, S2 to be the next smallest. So what we have is 0 is less than S1, S1 is less than S2, etc., all the way up to the last one, St minus 1. And then A to the 0 we kind of exclude from that. So what do I claim? I claim this should be my generator for S. So suppose not. What does that mean? I think that means there exists some index I'll use set notation instead of an interval. Some number I between t and t minus 1 with a to the si not beside a to the s1. Obviously, I can't be 1 because of s1. Well, that's not going to work for that. So that makes sense. Again, we've listed h is finite, so we can list all the elements in it. We pick the smallest integer that's positive, that's power, that's of a, that's in this. So we keep, and if we hope, what I claim is this element generates the whole group. If not, one of these other remaining elements can't be in that group. So what does that mean? Let's now apply the division algorithm. So we have S sub I equals Q S1 plus R with 0 less than R less than A1. Sorry, 0, yeah, strictly less than. Okay, now you say, wait a second, Blau, this is S1. The division algorithm implies that R can't be equal to, could be equal to 0. But if R is equal to 0, Si is, we'll see why that happens. So basically, this will assume why R can't equal 0. I'll have to argue that in a second. So let's come to why that R cannot equal 0. So let's suppose that was equal to 0. If R equals 0, then what do we have? We have a to the si. Well, R is 0, so that's S1 times Q. In other words, that's a to the S1 all raised to the Q. But that's an element in the cyclic subgroup generated by a to the S1, contrary to a to the Si not being in this subgroup. Thus, R would have to be positive. But then, in such a case, a to the R would be a to the R would be a to the Si minus QS1, which would basically be a to the Si times a to the S1 to the negative 1. But this is an H. A to the Si is an H. A to the S1 is an H, so the inverse would also have to be an H. So this would have to be an element of H. A contradiction since S1 was the smallest positive power of A in H. Right? Remember, we lined these up, so we picked it so that the Si is the smallest. All the remaining exponents, all the remaining, well, here's 1, 2, all the remaining t minus 2 exponents all have to be greater than S1. So that's a contradiction, right? In other words, A to the R would have to equal one of these, so that would mean R would have to be bigger than S1. So that's a contradiction. Thus, the only way out is R would have to equal 0. Well, really, there's no such element of H not in the cyclic subgroup generated by A to the S1 can exist. So we've proven that H is cyclic. So H equals the cyclic subgroup generated by A to the S1. H is cyclic. Okay, so we've proven that every subgroup of a cyclic subgroup is cyclic. Now let's prove the other part. Let K be a divisor of the order of G, which we have M. So we have M equals KD, where D is an integer. I mean, everything's positive integer. So we showed already that A to the D is equal to, the order of A to the D is equal to K. Thus, the cyclic subgroup generated by A to the D is a subgroup with K elements. So we've shown for each divisor of the order of a cyclic group, we have a subgroup with that many elements. Let us show this is the only one. We only need to show any subgroup with K elements, any subgroup, let's call it H again, with K elements, is the cyclic subgroup generated by A to the D. So we've already shown, in our proof, we have shown H of H is the cyclic subgroup generated by S, where S is positive and the least positive integer with A to the S in H. Again, going back to what is A, let's not forget our whole group G is cyclic, so a finite cyclic with M elements. So every element of G is either the identity or A squared all the way up to A to the N minus 1. So what do we have then? Is we have so we have, let's again using the division algorithm, M equals QS plus T with Q and T integers, and T is greater than or equal to 0 and less than S. By dividing through S, So what's then going to happen? Then we have the order of A equals M, so this is where A to the T, seen a similar argument to this, is A to the S inverse A to the M. Let's see, A to the T, is that right? T equals M times A to the, I think this would be A to the QS inverse times A to the M. So this would be A to the S to the negative Q times A to the M is the identity, so times the identity. So we just have some power of A to the S. So this is an element of H. But since T is less than S, it can't be a positive number, right? S is the least positive number. So it's greater than or equal to 0, but if it's less than S, it can't be positive, so T would have to equal 0. Otherwise, we'd have a contradiction. We'd have a positive number less than S, whose exponent took us, that's the, we raised A to that power, puts us in H. So we have T equals A to the S, so what does that mean? That means that M would then be Q times S. And so what does that tell us? I guess that tells us that the GCD of M and S, well, that tells us that S divides M. So the GCD of S and M has to be S. Again, remember, S is certainly a, we know S has to be less than M, or less than or equal to M, since if S was M, A to the M is the identity. So that's certainly in H. So we have this. And so what can we conclude then? Then we have that the GCD of of D and M. Again, GCD is the greatest common divisor of D and M, and that was equal to K. Which is the order of H, which is the order of the cyclic subgroup generated by this, which is M over the GCD of S and M. So that would be QS over S, or just Q. And so that would, and Q is the greatest common divisor of S and M. So again, let's kind of review these, make sure we see where these all come from. Initially, way back in the beginning of the proof, we had that K was a divisor of M. So we also had M equals K times D. So D divides M, so D would have to divide itself. Oh wait, so that's the so the greatest common divisor of G and M would be G and M would be K. Yeah, okay, that's what this is. It's K. No, not K. The greatest common divisor of D and M would be D. So that should follow through. So why is this unique here? So it's in the notes. So this would equal that. Right. I mean, ultimately, what we'd like to see is that we want to show that H is equal to D. So we've shown that we'd like to show these two are equal. So what do we have to show by the corollary? That their GCDs are both equal. So let's see why we have shown that. So let's temporarily scratch all this out. And see why A to the D would have to be the same as a cyclic subgroup generated by A to the S. So what we want is we want if the GCD of S and M is equal to the GCD of D and M, then these two cyclic subgroups are equal. That is, H, which we think of H as being an arbitrary cyclic subgroup with K elements, is in fact generated by A to the D. Okay, this argument we've completed up to here. This last line has proven that T is equal to 0, and so H is exactly this cyclic subgroup generated by A to the S. It just, maybe it's different than this cyclic subgroup. We're claiming it's not. So let's see why this is the case. So the GCD of S over M, by that thing, since T was equal to 0, M equals Q times S, so the GCD of S divides S divides M, we won't get any bigger than S and divide it, so this would just have to equal S. Which is M over Q. But what is the order of this M over Q? That's what it is. This is just equal to the order of H. Right? Because that's how we can get a cyclic, that's how many, the order of H is K. So if there's a K elements, M is equal to N over D. So this is equal to the order of H, but that's also got to equal M over K. That would also equal M over K, which is just D, which is again the GCD of D and M. So again, that's how it's proven from that. So this element S is M divided by Q, but that's got to be the same. The S is just how many elements are in the cyclic subgroup, or sorry, M divided by S is the size of the cyclic subgroup generated by H. So that proves that not only is A to the D a subgroup with K elements, it's the only subgroup with K elements. Okay, so we'll close with some examples. Okay, so let's look at some subgroup graphs. Again, we've done some of these in class. For example, order of G is 10. G is a cyclic group. So it's got to be generated by something. Let's call it A. So at the top we have A, and at the bottom we have the identity E, which if there are 10 elements, we know A to the 10th is a subgroup generated by the identity. Then this theorem says we can get each subgroup for each order, there's only a unique subgroup for each divisor of 10. So 2 is a divisor of 10. So to have an element fitting to K, if we go back to the proof of the theorem, K is equal to 2. So what was the order? It was A to the D, where D is equal to M over K, 10 over 2, or 5. So A to the 5th would be an element of order 2. And the cyclic subgroup generated by A to the 5th would be in order 2. What's another divisor would be a 5-element order cyclic group. So again, that would be similar. D would be 10 over 5, would be A squared. So A squared is a second subgroup. Let me maybe, there were some questions about these last time, so let me run through them carefully. So you have A to the 5th, A to the 5th times A to the 5th, or A to the 5th squared. Well, that is A to the 5th times A to the 5th. A to the 5th cubed, etc. It goes on forever, but there's only 10 elements, so it's got to stop. Well, this is A to the 5th times A to the 5th is A to the 10th, but that's the identity. So we just have A to the 5th and A to the 10th, which is the identity. If you looked at another power, what would A to the 5th cubed be? That would be A to the 5th squared times A to the 5th. But A to the 5th times A to the 5th is the identity, so that would be E times A to the 5th, or just A to the 5th. So this would be A to the 5th quantity cubed. Then multiplied by A to the 5th again, so A to the 5th to the 4th would still be A to the 10th. So again, this would be the subgroup, and I think we sometimes put the order up here. There's 1 element, 2 elements, 5 elements, and 10 elements. So that's a complete subgroup graph for a subgroup of order, a cyclic subgroup of order 10. We can look at what are some other subgroups. You say, wait a second. Well, I don't know. I don't buy this theorem. Maybe there's not maybe there's more subgroups that we're missing. So let's go through all the elements. Well, A, we've already got that, A squared. You say, what about A to the cube? What does that have? Now again, if we apply this theorem, the greatest common divisor of 10 and 3 is 1. So then A to the 3, the order of that would be 10 divided by 1, or all 10 elements. So this should be A to the first, because 1 and 3 both have the same greatest common divisor with 10. Let's just run through. So we have A cubed. Then we multiply it again, we have A to the 6. Then we have A to the 9th. Then we have A to the 12th. But what is A to the 12th? That's A to the 10th times A squared. But A to the 10th is the identity, so it's just A squared. So far we've got 3A cubed, A to the 6th, A to the 9th, A squared. Again, remember the fact that it's a cyclic subgroup of 10 elements generated by A, there has to be some generator, so G is just basically A to the first, A to the second, A to the 9th, all the way up to A to the 10th, which is the identity. So then you say, well, the next time then, it should be A to the 15th, but A to the 15th is A cubed, maybe times A to the 12th, we just saw as A squared, so that would give us A to the 5th. So maybe I won't run through all of it, but you can kind of see why we would have the subgroup generated by all powers of A is the same as the subgroup generated by all powers of A cubed. And so we've already listed that subgroup. Let's look at another example, A to the 4th. Say, wait a second, I don't see A to the 4th there. Where is that subgroup? Well, what's in A to the 4th? Well, A to the 4th, A to the 8th, A to the 12th, so I can slide over to that board or point to that board. A to the 12th is just A squared. Then I multiply it by 8 equals. Then the next would be A to the 16th, which would just be multiplying A squared by another A to the 4th. So that would give me A to the 6th. Then to get the next power, I multiply A to the 6th. I raise this by multiply by A to the 4th one more time. That would give me A to the 10th. That's the identity. But if I look at those elements, if I look at this would have A squared, A to the 4th, A to the 6th, A to the 8th, A to the 10th, the identity. Not in the same order, but the same elements. So this subgroup, we've already got listed. It's right here, the 5-element subgroup. And again, we note that the greatest common divisor of 10 and 4 is the same as the greatest common divisor of 10 and 2, and so that's why there's only one subgroup. So these two may look like two different cyclic subgroups, but when we actually list the elements, we see they're not. They contain the same elements. So let us look now at a cyclic group with 8 elements. And look at the subgroup lattice for that. Well, lattice, I guess I use also the term subgroup graph. So G is cyclic with 8 elements. And so since G is cyclic, G is generated by some element of order 8. So that gives the whole group, and the identity subgroup is down at the bottom. A to the 8th, which is the identity. A to the 8th is the identity, and that has to be the smallest power. since the order of A is the same as the order of the cyclic group generated by it, and there's 8 elements. So one divisor, what's the divisor of 8? There's 1's a divisor of 8, 8 is a divisor of 8, 2 and 4. So 2, what's in A squared? What would be an element of order 2? We take 8 divided by 2 is 4. So the order of A to the 4th is going to be 2. Right? A to the 4th times A to the 4th is just A to the 8th, the identity. And what about an element of order 4? A to the 4 divided by 2, that would be A squared. The cyclic subgroup generated by A squared is 4. So you have A to the 4th. And that's contained, so we'll make this a little bigger. That's the identity with one element. We would put an A to the 4th here, that has 2 elements. And in between here, we have an A squared that has a single element. Notice how it's a little bit different than a subgroup because here we have disjoint subgroups. Not disjoint, they have the identity in common, but there's not proper containment. One is not inside the other. There may be some overlap, but actually I don't think there is. No overlap, no containment. Here we have kind of containment. Again, you might notice that 10 is built from 2 different primes, whereas 8 is built from just a single prime, too. So in some ways, as we'll hopefully get to as we go throughout an algebra sequence, eventually one sees how these cyclic groups, in group theory, they help decompose groups the same way that prime numbers help decompose regular numbers. And then I think I looked at an order of 8 elements, but I said an order, it's mislabeled in the notes, but it's 12 elements. The subgroup graph is right. So we can look at G cyclic with the order of G being 12. So if it's cyclic, it's got to have a generator. So we have some divisors. Down here we have 1, and up here is 12. What else divides 6? What divides 12? 6, 4, 3, and 2. So way at the top we have our 12 element, and down at the bottom we have identity. What about an order of 2? What element has order 2? If A to the D would have order 2, that would mean 12 divided by D would have to be 2, or 12 divided by 2 is D, so it would be A to the 6th. So we have A to the 6th. Then what about we have A to the 3rd? 12 divided by 3 is 4, 3 element I should say, so A to the 4th would give us our second subgroup. So let's see, is this included? What is in A to the 4th? A to the 4th, A to the 8th, and A to the 4th, one more A to the 4th will give us A to the 12th, which is the identity. A to the 6th is just A to the 6th in the identity, so there'd be no overlap, so maybe I'll draw it up here at this level is A to the 4th. Then what 12 divided by 4 is 3. What about A cubed? A cubed would have 4 elements. A cubed times A cubed is A to the 6th. A to the 6th cubed again would be A to the 9th. A to the 19th, A to the 9th. A to the 9th times A cubed would give us A to the 12th, which is just the identity. So that would put us up here at the 4 level. And that does contain A to the 6th, right? A to the 6th has these 2 elements, so that subgroup is contained. Last one is 6. That would be what? A squared, which would certainly have, it would have a squared, a to the fourth, a to the sixth, a to the eighth, a to the 10th, and then a to the 12th, which is the identity, because the order of A, well, the order of G is 12. G is generated by A, so the order of A would have to be 12. So that means A to the 12th is the identity, and that's the first power. We look at A to the third. There's some overlap, but there's not containment. A to the third is not directly contained in this. A to the fourth would be. A to the sixth would be. So, I don't know how to best draw this to our line here. These can like intersect, so that's A squared, and then this would go up, and this would go up. So this cross and this, it's not a graph here or anything. That doesn't really hold any relevance. Just this is contained in A squared. And then we're trying to get 6 can go up. 6 is contained in A cubed. And the 6 is also contained in A squared. But this is not contained in that. So again, as you can see, there is some overlap. Namely, well, of course there's some overlap. A to the 6 is inside both of these. Whereas you can see A to the 4th, is there any overlap with A cubed, with those subgroups generated? And well, yeah, I mean, every subgroup has some overlap. Every subgroup has the identity in common. So we'll conclude with a couple of theorems. You're kind of using Lagrange, you're getting some results about cyclic groups. So theorem, let G be a group of order P, P a prime number. Then G is cyclic and has no non-trivial subgroups. No subgroups except for what? Well, what are the trivial subgroups? Certainly the identity is a subgroup of G, and the group itself is a subgroup, but nothing in between. In other words, a subgroup graph would be a single straight line from G to the identity. That's all, folks. So let's prove. So we're going to use a prime. What is important about prime? Primes don't have any divisors. And Lagrange links the order of a subgroup to the divisors. So also 1 is not a prime number, right? 1 is neither prime nor composite. So P is greater than 1. Let me scoot this over. So the number of elements of G, which is P, is greater than 1. So there exists an A in G with A not equal to the identity. So the cyclic subgroup generated by A can't just contain the identity. It's got more than one element. But the cyclic subgroup generated, but the order of A, which is the order of the cyclic subgroup generated by A, divides P. So that tells us that if it's not 1 and it divides P, it's got to, I probably should put, so the order of the cyclic subgroup is greater than 1. But if it divides a prime and it's greater than 1, it's got to equal prime. So thus, G is generated by this non-identity element. Again, this is Lagrange's theorem. Where did Lagrange's theorem show up? That the order of an element, this is the same as the order of the cyclic subgroup, it's got to divide the order of the group, which is a prime. So now let's take any subgroup of G, the order of G divides P, so either, the order of H divides the order of G, so the order of H divides P, so either H equals P or H equals 1. So either H is all P elements of the group, or H consists merely of the identity. Okay, so let's conclude with the last thing that we've got in this note, theorem. Let G be a group of order 4, either G is cyclic or every element of G is its own inverse. Okay, let's look at the proof. If there exists an A in G that has order 4, then that cyclic subgroup generated by A has to be all of G, and G is cyclic. If not, since order of A divides 4, the order of A equals 1, or the order of A equals 2. If the order of A equals 1, only one element has order 1, A is the identity, and so certainly A squared is E squared, which is E, which is A, so A inverse is equal to A. Well, maybe I don't even need to show that the identity is its own inverse. If the order of A equals 2, then A squared is E, so A squared times A inverse equals E times, or equals E times A inverse, or just A would equal A inverse. So either we have such an A with order 4, or if not, if not, then this is true for every, okay, if there doesn't exist an A with order of A equals 4, the above holds for all A and A. All right, so we'll conclude right there, and we'll be picking up with a lecture soon on the integers mod n.